We're in the middle of talking about how to generate power series last time with derivatives and integrals. So there are constructive ways to make a power series, which we call a Taylor series. When we take our function and we take repeated derivatives and we build the coefficients, so we sort of construct the power series by taking all these derivatives and dividing by the factorial and making the power series. Another way to build power series is to take a known power series and take a derivative, take an integral, multiply it by a function of x or something. And that's where we are right now. We're going to be differentiating and integrating. And one important thing when you're differentiating or integrating is that the interval will not change, the goalpost will not change, but you might lose or gain convergence at the end points. All right, so differentiating or integrating, if your interval of convergence went from -2 to 2 for the one that you are taking the derivative of, then the interval is still going to go -2 to 2. But you have to check the endpoints. A lot of times when you integrate, you will gain convergence, and a lot of times when you differentiate, you will lose convergence at endpoints. So we just have to test. So we've got our classic, most important power series that we've seen so far, the geometric series power series. And we've got this function g that looks a lot like f. And what we want to do is try to build a roadmap on how to get to g from f. How do we get to g from f? So we've got this known power series. We want to differentiate or integrate f to get to g and then do it to the power series. So do you think we're going to differentiate or integrate f to get over to g?
Differentiate.
Differentiate is going to be the key, because if you think about 1 over x, if you have the function 1 over x and you differentiate, don't you end up with -1 over x to the 2? Right? When you differentiate 1 over x, the power in the denominator starts growing. And that's going to be the key here, is that we differentiate. So let's just start with f. And let's see, we're going to try to build g from f and then just keep track of what we're doing. It's always easier to differentiate when you have it written with an exponent. So let's write this as 1 minus x to the -1. And then when we differentiate it one time, the minus comes down. I should put it in front. The minus comes down. We subtract 1 from the exponent. So that's the power rule part. Power down, subtract 1. And then we multiply by the derivative of the inside, the chain rule piece. So we multiply by -1, and that makes this positive. And you can see we're getting closer. This is a power of 3. So if we take one more derivative, we're going to end up with -2 times 1 minus x to the -3. Once again, we have to then do the chain rule part where we multiply by the derivative of the base. Multiply by -1, we get that. And there we are, right? This is g, almost, but we are right there with the denominator. The denominator is exactly what we want. Okay, so that's f double prime. Now we're not quite to g. We have one tiny little manipulation to do left, and that is divide both sides by 2. If we divide both sides by 2, then we end up with 1 over 1 minus x quantity cubed. That is g of x. Right? G is 1 divided by 1 minus x cubed. So as soon as we take our second derivative of f, if we divide both sides by 2, now we have g. Now we can create the power series for g by taking the power series for f, differentiating twice, divide by 2. And that'll give us power series for g. And then we'll have to test our endpoints. So let's see if we can do that. So we come over to our power series here. So this is the power series for f right there. So let's say that that is f of x equals this power series. Starts at 0, x to the k. There's f. Differentiating? Simple. It's polynomial. Pull down the power, subtract 1. So f prime, we pull down the power and subtract 1. That's not too bad. Polynomial differentiation. Now let me ask you, what does the k value start at? Does the k value still start at 0, or does the k value start at a different number? Note that if you plug in k equals 0, you get x to the minus 1. That's not good. We need to start from 1, because when we plug in 1, we'll get x to the 0, which is 1 times k. If you look up here and you differentiate, derivative of 1 is 0, derivative of x is 1. So what it tells us up here when you look at that is that the very first term here should be a 1. Right? Because the derivative of 1 is 0, derivative of x is 1. So the f prime power series should start with a 1. Well, if we put a 0 in here, we get an x to the negative 1, which is not a polynomial. But if we start at k equals 1, then we get x to the 0, and we get a 1 right there, we'll get a 1. So we get the right thing. And this, in your mind, if you think about taking x squared plus x plus 1 and differentiate it, doesn't that lose a term? If you have x squared plus x plus 1, you end up with 2x plus 1, so you went from 3 terms to 2 terms. So it's that idea. When you differentiate and you have all powers represented, the constant term vanishes, disappears. So you end up with 1 less term. Okay, there's f prime. F double prime. Again, it's a polynomial. That's not too bad. So with a polynomial, we bring down the power, we bring down the exponent, and subtract 1 from the exponent. And once again, we can't have a negative exponent on x. That's not a polynomial. X to the negative 1 or x to the negative 2 is 1 divided by x, or 1 divided by x squared, not a polynomial. And we know that when we differentiate a polynomial, we get a polynomial. So we're going to have to start at 2 here. So every time we differentiate, we're losing a term. All right, we're almost to g. So last step, therefore, g of x will equal f double prime divided by 2. So we're going to put a 1/2 out in front. This is going to start at k equals 2. And we have k times k minus 1, x raised to the k minus 2 power. So there's our power series for g from f. Last step is that we have to now calculate the interval of convergence. So when you differentiate, the goalposts stay the same, -1 and 1. That stays the same. Now we have to test the endpoints to make sure we didn't gain convergence. We might have a bracket. If we did gain convergence, we might have a bracket. So let's double check. We plug in -1. So we come over here. So we're going to test the endpoints. So x equals -1. We plug that in here. And it has the 1/2 out in front. We know that constants don't change convergence or divergence. You can put the 1/2 or leave the 1/2 off. It doesn't matter. Does not matter. So I'm going to ignore the 1/2 and look at this. So I'm plugging in -1 raised to the k minus 2. So we need to know, does that series converge or diverge? First off, tell me, is this an alternating series or not an alternating series? This is a series of numbers. Is it alternating or not alternating?
Alternating.
It is alternating. This is a switch. When you plug in 2 or 4 or 6, you have an even exponent. When you plug in 3 or 5 or 7, you end up with an odd exponent. So we have -1 raised to an exponent that's switching between even and odd, so it's definitely a switch. With an alternating series, this part right here is the a sub k. Now, for an alternating series, the negative sign is not part of the a sub k. So that is a sub k. What is the limit of a sub k right there? What's the limit of a sub k as k goes to infinity?
Infinity.
Do we agree? K times k minus 1 as k goes to infinity? It's going to go to infinity. Is that 0? No. So that means we have divergence. Right? The divergence test says if a sub k's limit is not 0, the series diverges. End of story. So this is going to diverge by divergence test. So the limit of a sub k is non-zero. If it's non-zero, diverges. All right, now let's test the other endpoint, and we're going to have something similar. When we test x equals 1, plugging in 1 here, the series becomes, doesn't even matter where it starts, we'll put a 2 there anyway. So we get k times k minus 1. 1 to any power is 1. Same thing, right? There's your a sub k. This is going to diverge by the divergence test. Diverge by divergence test. So our final piece of work up here is that our IOC, our interval of convergence, is -1 to 1. We did not gain any convergence at the endpoints. So both those endpoints diverge by divergence test. The only way a series of numbers can converge, at the very least, the terms have to go to 0. If the terms don't go to 0, you know it diverges. Any question that you want to ask on that? Any piece of that you're not sure about? So we build a roadmap from the known power series to the new function, and then we just do that. Yeah?
How many more of these known like functions are there?
Well, we have 12 that we need to know, 12 that we're going to work with.
Okay.
So
we have to, are they always given to us, or we have to memorize?
Some of them you have to memorize. So for the exam, I'm going to pick 5 that you have to memorize. I'll tell you those on which ones you have to memorize. Yeah, so on Tuesday, I'll tell you which ones you definitely have to have memorized. One of them, the geometric series and the exponential function, for sure. Those are the most important two. Geometric series and exponential function. So those for sure. All right, so let's take a look at this one. This function, when we stare at it, we know that that's not the geometric series, but it is related to the geometric series. We can build the power series for f pretty easily by manipulating the power series right here. Okay, we'll do that in a second. Our first goal, though, is to build the roadmap from f to g. And do you think we should integrate f, or do you think we should differentiate f to try to build g?
Integrate.
Integrate. So we're starting with f, and if we integrate f with respect to x, we're going to integrate that. It's almost in log form. We need a 2 there and a 2 in the bottom out there. Now it's in log form. Right? Now the derivative of that denominator is the numerator. So that's great. That is great news, because we know how to integrate. That's going to be the natural log of the absolute value of the denominator. Well, we don't need absolute value bars because that's always positive. Right? That's log form, natural log of the absolute value of the denominator if you're in log form, plus some constant. Okay. Now, the question that we have to ask ourselves is, how do we get to this? How do we get to that? So we want to get to that. And the idea will be that if we multiply both sides by 2, we're going to get over here. Right? So that 2 is going to come to the left-hand side. So if we do 2 times the integral of f of x dx, then over here, we're going to have natural log of 1 plus x squared plus a c. If we multiply both sides by 2, it's still just a constant. It doesn't matter that we don't have to change. We can just still use a c to represent the constant. Okay. Now, we'll talk about that constant in a minute. We'll see that we can pick it to be 0 in a minute. But what this is telling us is that we almost have g. Right, there's g right there. We have g plus c. We'll just have to reconcile that constant, which we'll do in a minute. The first thing, after we get this roadmap to get to g from f, we need to get our power series for f. So let's do that. So there's our geometric series. What is the power series for f? So f, we look at that power series up there. The first thing we have to do is replace this x with negative x squared. So if we turn all these x's into negative x squared, then we'll have the power series for 1 over 1 plus x squared. So that's the first thing. So we're going to replace the x with negative x squared. So negative x squared is going in for that x right there. Okay. So that's going to give us the power series for 1 divided by 1 plus x squared. But then we have this x in the numerator, so we have to multiply by x. This power series here doesn't have an x in the numerator, so to force it to have an x in the numerator, we just multiply by x. So we're going to multiply by x, and if we multiply by x, we can put that right on the inside, right there. Multiply by x. This is now the power series for f. Replace x with negative x squared, and multiply by x. And this starts at 0. Okay. Now the interval of convergence for this one. Let's talk about that. Let me simplify what's inside here first, and then we'll talk about the interval of convergence for it. So we have negative 1 to the k, x raised to the 2k, plus 1 if we combine the powers of x. So what we learned last class was that when we do a substitution, you have to do the same substitution into the interval of convergence. When you multiply by a power of x, we saw last time that it doesn't change the interval of convergence at all. So the multiplication by x isn't going to change anything with the interval of convergence, but this substitution could. So we take our interval of convergence that we started with, so negative 1 is less than x, which is less than 1, and then we replaced x with negative x squared. So when we do that, we're replacing this x with negative x squared, and we have to see what happens. So whatever we did for our substitution into the power series, we have to do it into the interval of convergence also. So the first thing we do is multiply this by negative 1, and we have that. When you multiply by a negative, you have to change the direction. Well, this is really nothing more than, let's put it in the correct order. It's easier to read an inequality when it is in this order, right there. And so this says we want the x's so that x squared is between negative 1 and 1. X squared is always greater than negative 1. So it's really the right-hand side that's going to be what we have to decide. So let's take a look at the graph. I did this with a picture the other day, and I'll do it again. So there is a picture of x squared, and we want x squared between negative 1 and 1. So there's 1, there's negative 1. So x squared is the y values. It's the function. We want it between negative 1 and 1. And so we just are looking at the x-axis here, and we see that, well, if we go to negative 1 and don't include it, and then we go all the way over to positive 1 and include it, those are going to give y values that are between there and there, between negative 1 and 1. So our x must be somewhere between negative 1 and 1. If we pick an x value between negative 1 and 1, not including the endpoints, we will end up with a y value that's between negative 1 and 1. Okay, so that's going to be our new interval of convergence, which isn't that new because it's the same as the original one, but we had to show that. Okay. So now, we are trying to find this power series for G, so this thing right here. We need to integrate the power series for F. So let's integrate the power series for F. So the integral of the power series for F. We know how to integrate, it's just a polynomial. We add 1 to the exponent, divide by the new exponent. All right, -1 to the k, that's a constant. Right, you don't do anything with a constant. When you're integrating a constant times a function, the constant just drifts along. It's a freeloader, just coming along. This is the x part. This is what we have to change. We add 1 to the exponent and divide by the new exponent. There we go. So there's our new power series. Now we have to check the index value, where it starts. So up here, tell me what the very first term up here is. When you plug in 0, what is that term? It's +1, plugging in 0 there. And when you plug in 0 there, you get x to the 1. And what's the integral of x to the 1? X squared over 2. So that should be the very first term in this integration of that power series. When we plug in 0, do we get that? If we plug in 0,
Yes.
do we get x squared over 2? Yes. We plug in 0 there, we get x squared. We plug in 0 there, we get 2. We plug in 0 there, we get a positive. So we do not have to adjust the index in this case. Sometimes you do, sometimes you don't. You just have to make sure that the first term does what it's supposed to do. The first term here is +x. Integrate, get x squared over 2. That's what you need to have as your first term right there. Okay. Now, when you integrate, you get a plus c. Okay, so let's ask ourselves about the function and whether we can figure out what that constant of integration is. So we did this integration, we get a plus c. When we look at the function, let's see, where do I want to look? So if we look right here, this function right here, if you plug in 0, what is f of 0? F of 0, you plug in a 0 there and there, you get 0. You get 0 over 1. If you plug in a 0 for this x, f of 0 is, what's the value of f of 0? If you plug in 0 here and you 0 there, you get 0 over 1 plus 0. So you get 0 over 1, which is 0. So that's the value of f at 0. Okay, so what is the value of g at 0? Same thing. If you plug in a 0 right there, you get natural log of 1, which is 0. So when we look at this, so this right here, we know that if we plug in 0 right there, we get 0. Okay? On this side, with f, we also get 0. And so that tells us that this constant must be 0. Because both f and g evaluate to 0 when you plug in 0. So there's not an extra constant that is going to come into play. This constant will have value of 0, so we can ignore it. We'll do another one as we go, and we can talk a little bit more about it. So we are not quite to g yet. What do we have to do to the integral of f to get to g? Multiply it by 2. So g of x is 2 times the integral of f of x. So then all we have to do is continue that multiplication all the way through. And we have this. That is our power series. So now we have our power series for g. And the only thing we have left to do is that we started with the power series for f. We got the interval of convergence for f. But then we integrated the power series for f, which means the interval needs to be tested at the endpoints. The interval is going to be the same, in terms of the goalposts, negative 1 to 1. Now we just have to test those endpoints. So we're going to come in here and test x equals negative 1. We're going to test x equals positive 1 and see whether we have convergence or divergence. So let's first plug in negative 1. And again, it doesn't matter that there's a constant being multiplied. That does not affect convergence. It doesn't matter where the series starts. That does not affect convergence. What matters is the guts here. So we have negative 1 to the k. Plug in negative 1 here. Negative 1 to the 2k plus 2. What is the value of negative 1 to the 2k plus 2? Is it a switch? Or is it always positive 1, or is it always negative 1? You have 3 choices. So when you plug in negative 1 right there, what do you get when you simplify that?
It's always positive.
It's always, so the exponent's always even, which means it's always going to be positive 1. Yes, always positive. All right? So that means that these two things, you don't even want to combine these things. That just turns into a plus 1. So the idea then is that we have an alternating series right there. Alternating series. Does that alternating series converge? So there is your a sub k. Is the limit of a sub k 0?
Yes.
Yeah. Do the a sub k's get smaller as you go? So as you pick bigger k's, do the fractions get smaller? Yeah. You plug in k equals 2, the denominator is what it is. You plug in k equals 3 and it's bigger. You plug in k equals 4, it's bigger. So the terms are going to 0. So the terms are decreasing and going to 0. And we don't have to be that specific. In chapter 10, when you do the alternating series test, you have to show me the 2 steps. Here you can just say converge by alternating series test. You don't have, you can just intuit it.
I noticed on some of the questions on the homework, instead of saying like the function was decreasing, it would say it's non-increasing. But that's the same thing as decreasing, right?
Essentially, for us it is. To create a function that is non-increasing, that means it's flat or going down. The only way we have to do that is to create a piecewise defined function. There's no common function that can be flat and then go down and then flatten out again. So for us, when we see non-increasing, we think decreasing.
Oh, okay.
Because to add, the most general principle is yes, it can be non-increasing, but in practice, it's always decreasing. Like we don't have the sophistication to build these functions that can do weird things like flatten out and then continue down.
So if it's approaching 0, you'd say it's non-increasing?
Yes.
Then?
Yeah.
Okay.
So this function is decreasing, and every decreasing function is non-increasing.
Okay.
A function that's decreasing never goes up, which is what non-increasing means. Non-increasing means it never turns and goes up. So it's either flat or going down. So decreasing is the nicest type of non-increasing. So this function right here is decreasing to 0. And that's all you need for an alternating series to converge. If the a sub k's decrease to 0, that alternating series converges. If it was a series that was not alternating, that's not enough. But when it's alternating, all you need is the terms decreasing to 0. But if the terms are positive, then that's all bets are off. Because we see 1 over k approaches 0 in a decreasing way, but that series diverged. So the alternating sign is key. That gives us that extra boost, that all we need is that the terms go to 0 and they're decreasing. So that converges by AST. And then when we plug in 1, let's see what the series is. We have negative 1 to the k. 1 to anything is 1. Oh, we end up with the same series. So both of these are going to converge in the same exact way by AST. That tells us that our interval of convergence is going to be same goalpost, negative 1 to 1, except we now include them.
And did you say usually when you're differentiating, you'll lose and integrating you'll gain
Yeah,
generally?
yes. Generally, it's very rare to differentiate and gain an endpoint, and it's very rare to integrate and lose. Yeah, but we don't always gain or always lose, but yeah.
So, is there another way to find the interval of convergence?
No.
No, that's the only way? Because
You could.
Or there was another.
Well, if you want to spend a lot of extra work, you could do the ratio test on this. So the whole point about what we did on Tuesday, when you do this substitution thing, is that you don't have to then go do the ratio test again. The substitution thing gives us your new interval of convergence. But then when you differentiate or integrate, that interval of convergence stays the same with the goalposts, but you have to differentiate, but you have to check the endpoints. Whenever you differentiate or integrate, you could have a change at the endpoints. If you wanted to, you could just take this series from scratch and say, hey, I'm just going to do the ratio test on this. That is 5 times as much work, though. Like, the whole point with a derivative or an integral is that you don't have to do that. You can just take the prior interval of convergence and do 2 endpoint tests. Because if you were to do the ratio test, you would have to test the endpoints anyway, but then you would have to go through the whole, ACE, you plug in the k+1, divide, take the limit, and then test the endpoints. So part of what we learned on Tuesday is that you have a shortcut to the interval of convergence. If you differentiate or integrate, you just test the endpoints. And if you do a substitution, you plug the substitution in. Because the same thing holds here. You could redo the ratio test on this right here if you wanted, but that's 5 times as much work as just plugging in the substitution into the old interval of convergence. So, yeah, it definitely is not the way you want to go. Okay, so let's try a couple more. So the derivative and integral ones, those are the sort of the trickiest ones. There's a lot to them. These ones, there's less work, but we have to do some manipulation. Quite frequently, we can manipulate a known power series if the center is 0. If the center is not 0, we're going to see that you can't always just do what we're about to do here. So this power series has a center of 0. We want a power series for this. So my first question to you is, this function is always positive, right? We have a positive 1 in front. If we want to try to use this power series over here, the first thing we want to do is force that to be positive. So we're going to multiply both sides by -1. If we multiply both sides by -1, that negative is going to move over to the front of that infinite series. All right, good. What are we going to replace the x with? Replace it with? We have an x squared here. We have an x there. So the power series has just an x, so we want to replace it with x squared. So we can build the power series quite quickly for this. So natural log of 1 minus x squared. So that power series, we multiplied by -1. So we're going to put that in front of the summation. Starts at 1. And we replace the x with x squared. So if you replace the x with x squared inside the summation, you now have that. All right. How do we get the square root? So we need to get a power of 1/2 on the inside of this log. How do you get a power on the inside of a log?
Multiply by 1/2.
Multiply by 1/2. If we multiply by 1/2 out here, we multiply by 1/2 here. But then this 1/2 over here has superpowers. It can jump up and become the exponent on the inside of the log. So that's how we're going to get that square root, by multiplying and using a log property. And so now we have exactly what we wanted. So this is the power series for F. That's the power series for F. Now we included a substitution. We didn't take any derivatives or anything, so that's good. But we did include a substitution. So we have to come over here, and the original interval of convergence, the original IOC, is this. But then we did a substitution. Multiplying by -1 doesn't do anything. Multiplying by 1/2 doesn't do anything. But we did a substitution. We changed the x to x squared. So we have to do the same thing over here. We have to come over here and say, all right, the new IOC is going to be based on that substitution. And again, I think it's easiest if you think in terms of functions here. If you think in terms of functions, here's the graph of x squared. And we want x squared, we want that function to be between +1 and -1. So we want to know, hey, what are the x values that give this function value a number between -1 and 1? And so we do the same thing that we've done a couple times now. And we see that, oh, well, that really is just x equals -1 to 1. And we want to exclude these two because we got to be less than 1, not less than or equal to 1. And so if we are at 1, we want to exclude it so that that puts us right up here. That puts us right up there. So our x's have to be between -1 and 1. So we see that we lost convergence at -1. And so the IOC for this right here is going to be -1 to 1 with parentheses. So there is our power series with its interval of convergence. So the nice thing with these rules that we learned on Tuesday is that you do not have to go all the way back to the ratio test to figure out the interval of convergence. You can use the interval of convergence for the power series that you're manipulating. So here's another substitution one. So here, it's a little more straightforward. The only thing we're doing is turning all the x's into 4x squared.
If it's parentheses, it
Excludes.
no. But like, does it diverge or converge? Diverge.
So this series right here diverges at -1 and diverges at +1.
And then if it's bracketed, it converges.
Then if it's a bracket, it includes it. So it's included in the interval of convergence, so you would have convergence there. So this original series converges at -1. But then when we did this manipulation, we lost convergence at -1. So this series won't converge at -1. Which makes perfect sense if you look to the left side. If you plug in -1 on the left side, what do you get? If you plug in -1 on the left side, you end up with natural log of 0, which is undefined. Right? Natural log of 0 is undefined. Whereas up here, if you plug in -1, you end up with a 2 inside there, and natural log of 2 is, of course, defined. Right? So you sort of, there's always that extra check that you should be able to see by looking at the function side. With this one, we are purely doing a substitution. So this function f, all we do is replace the x with 4x squared. So let's go ahead over here. This is a series that starts at 0. It's an alternating series. And we're replacing the x with 4x to the 2. 2k plus 1 is the exponent, 2k plus 1. And then the interval of convergence, -1 less than or equal to x less than or equal to 1. So here's the original interval of convergence. We took that x right there and turned it into a 4x squared. There's the power series part. We'll simplify this exponent in a moment. But we have to do the same substitution over here. Whatever we substituted over there, we have to substitute right there. Got to do that. So our final form for this power series will be -1 to the k. Here we're going to have a constant of 4 raised to the 2k plus 1. And then that's multiplied by our power of x, which will be x to the 4k plus 2, divided by 2k plus 1. So there's the power series part. Usually we break it apart, get that coefficient away from the x so that we have the powers of x here. But now we have to come over here and adjust our IOC. So if we divide everything by 4, we have that. And now we want to solve this. We can't just take the square root of all the sides here. That doesn't work, especially with an even root. So again, I think looking at a graph is a pretty easy way to go. So if we look at the graph of x squared, we want the value of that graph to be between 1/4 and -1/4. So we want this, the function, to be between -1/4 and 1/4. So we have to figure out what those x's are that give us that. Well, x is going to be 1/2 or -1/2. And if you go up to the function, we want to be less than or equal to 1/4. So that means we can actually include, right? We can include the value there. Oops, that's a little too far over there. So there is -1/2, ... and that's going to be over to 1/4. So here we're going to include the left and right endpoint, whereas before we weren't in the last one. So -1/2 to 1/2. So -1/2 to 1/2. That will be our new IOC. So we've got our power series with its interval of convergence. So the main key here is that when you're doing a substitution, then you also substitute into the old IOC to get the new one. All right, any part of that you want to ask about for either of those? Let's take a look at, so we looked at these 6 power series last time. So these 6 are based on the geometric series. And I explained how you get to the next one in the beige box. The last one here is inverse tangent. And what I mentioned last time was that if you come up here to the geometric series and replace x with x squared, then you have 1/1 plus x squared on the left. And if you integrate that, you get arctan. And that's what this is. You replace all the x's with x squared, and then you integrate both sides, and you get that. So that is the arctan one. Now looking at that arctan one, just keep that a mental image of that. All odd powers, no factorials in the bottom, and it's alternating. When we look at our last 6 power series, last 6 of the common power series, just glance at sign for a second. Oh, that's identical to inverse tangent, except that this has factorials. So the inverse tangent power series, the sine power series are the same, except that the sine one has factorial. All right. So we've looked at this power series before for E. This is going to be the building block power series for this group of 6. Well, actually for 5 of the 6. So there's E. And many of you have seen this bizarre equation over the years. Can I remember the equation? Give me a second. I'll remember in a minute. It's coming to me. So, when you look at the power series for E, or you just imagine the exponential function in general, there's no hint that sine or cosine has anything to do with that exponential function. Right? When you do your math in Calc 1, even in Calc 2 up to this point, never have you sort of seen a connection between sine and e to the x or cosine and e to the x. Right? Never seen that before. There is a famous formula called Euler's formula that says that. It's the most famous formula in math, arguably, because it has the 5 most important math constants in one equation without any extra junk. Right? That's it. All 5 constants in one equation. Probably the most fascinating formula that we see in math. All 5 famous math constants written in one formula. And it turns out that this formula can be proven with power series. And it turns out that this e to the pi I thing is going to create some cosine and sine. And here's how. So when you look at the power series for e to the x, if you didn't know the power series for e to the x, you know how to construct it now. We did that last week. Take a bunch of derivatives, build the coefficients. You know how to do it now. You can build that. You also know how to build the power series for these two. Same thing. Take 5 derivatives, look at the pattern, build the coefficients, and you'll get the power series. When you look at the power series for sine and cosine, and then you look up at the power series for e, all of a sudden, you realize that there is a connection between the exponential function and sine and cosine. The power series for sine is all the odd powers with a switch thrown in. The power series for cosine is all the even powers with a switch thrown in. Okay. Now look at sine, cosine, and sinh and cosh. Power series for sine, power series for sinh, identical except no switch. Power series for cosine, power series for cosh, identical but no switch. Which is why you start to understand why they want to name the hyperbolics as they name them, because they are so closely related to the circular functions. So this group of 5 start with e to the, as soon as you know e to the x, it doesn't take much to memorize sine and cosine. Sine's an odd function, cosine's an even function. Take the even powers, you get cosine, take the odd powers, you get sine, and then just throw in a switch. And if you want sinh and cosh, you blow the switch out. This is the one that's an oddball. We're going to deal with that one later today. That's called the binomial series. So those 12 power series are the most important power series for sure. And I will pick 5 of them that you'll need to know for the exam. The 3 that we always have that are super important, e to the x, geometric series, and binomial. So those 3 are for sure on the test. When you look at this binomial thing, we'll get into the details in a minute, but it should look to you like a modified geometric series. Right? A geometric series, x plus x, no, it's on the other slide. 1 plus x squared plus x cubed plus x to the 4th, geometric series. Isn't that what that looks like? It's just you've got these weird coefficients, which we're going to talk about. So that one is not hard to memorize either, because it's just the geometric series with weird coefficients. And we'll talk about how to build the weird coefficients in a minute. Okay, so here's where we are so far. We've talked about all of this. When we have a function that you can differentiate, you can construct or build the power series by doing this. This is what we did last week. The only difference is that last week we built Taylor polynomials. This week we're building Taylor series. The only difference is ... So if you are asked on a test to build a Taylor series, make sure that you put the plus ... If you leave off the plus ... it's not a Taylor series, it's a Taylor polynomial. So this is just a recap of what we did last week. All we did was put dot, dot, dot now. Now it's a series instead of a polynomial. That's it. One terminology thing is that when the center is 0, it's called a Maclaurin series. This guy snuck in and got his name thrown into a Taylor series that just happens to be centered at the origin. That's all it means. So a Maclaurin series is just a Taylor series, but emphasizing that the series is centered at the origin. All right. For series to be useful, we need to know when the series converges. And more importantly, which is a very subtle point which we're not going to get into, when is the function, so there is a subtlety. You've built this series. Okay, you've built it from a function. F of x equals e to the x. Take all these derivatives. Build all these coefficients. You've built this power series. It's not trivial that the power series actually equals the function that you built it from. Right? So you start with the function, you take all these derivatives, you build this power series, you figure out its interval of convergence. There's one subtle step. Okay, we've got this convergent power series. Showing that it actually converges to the function that you use to generate it is kind of a big step. It is true that if you start with a function and you differentiate and build the series and the series converges, it does converge to that function, but you can't prove that until you get into higher math. So for us, we just are going to say that it's wherever the series converges, the series is converging to the function that you built it from. Okay, not totally trivial, feels kind of obvious, one of those subtle things. If you have a series, a power series, when we call it a Taylor series, it kind of implies that we created it from the function. We started with the function, took its derivatives, and built it. So if you find a Taylor series that represents a function, there is no other infinite series that represents the same function. So if you find another series that represents the function, it actually must be exactly the same. So each function is going to have its unique Taylor series. All right. Now, what we just did in the last hour, we were dealing with Maclaurin series. We were dealing with series centered at the origin, and we said, okay, we're going to start with the series and differentiate or integrate or substitute to get to a new series. If you are asked to find, and that's normally what you should do when the center is 0. If the center is not 0, we don't have like an index of series that are not centered at the origin. We have one series in that list that was centered at 1. But 90% of the series that we just sort of casually know are Maclaurin series. Bless you. They're centered at the origin. If you are asked to find a power series not centered at the origin, break out the hammer and nails and just start building it. Build it by taking derivatives and forming the coefficients. So if it's not centered at the origin, you've got to construct it. There's not this substitution shortcut method that we just have been doing all morning. So if we want a power series, a Taylor series, for this function, not at the origin, we got to go through the process. So we start with our function. We take our derivative. We do the table thing that we've been doing. And this says how many terms? It says the first 4 non-zero terms. So we just take down to the 4th derivative. And once we have our derivatives, let's see, that's 120 positive x to the negative 6. So this is what we did on Tuesday. We're just constructing it. So we're building the power series from its derivatives. And then we plug in y of 1 is 1, y prime of 1 is negative 2, y double prime of 1 is 6, y triple prime of 1 is negative 24. So when the power series is not centered at the origin, this is what we do. Got that? And then we are going to build the power series. This doesn't necessarily mean we're going to be able to see a pattern in the coefficients. On the exam, I will not ask you to find the summation form unless it's super obvious. Like if you have a bunch of coefficients, it's not obvious usually how to create the summation form. So I'm not going to ask you. There's a couple homework questions that ask you that. And it can take a long time to sort of discern the pattern. So for us, I will ask you for the expanded form. So our function will be 1 minus 2 times x minus 1. There's the tangent line. So we have the value of the function first, and then the slope of the function times x minus the shift. Now we go to the quadratic term. We're going to get plus 6 divided by 2 factorial times x minus 1 squared. So there's our best quadratic approximation. And we keep on trucking. Minus 24 divided by 3 factorial, x minus 1 cubed. There's our best cubic approximation. That's the best cubic. And this asks for 4 non-zero terms. Actually went a little further than we had to go. We don't actually need the 4th derivative, we just need the 3rd derivative, because that gives us 4 terms. If they asked us, like they would have on Tuesday, find p sub 4, p sub 4 we would need the 4th derivative. This is p sub 3, but p sub 3 has 4 terms. And p sub 2 has 3 terms. P sub 1 has 2 terms. So they said 4 non-zero terms, so it's okay to finish right here. That is a Taylor polynomial. We're not done. We're finding a series, so we do this. Now we've just found the series. So that's the only difference from Tuesday. Plus, dot, dot, dot. Okay, now this question is asking for the summation notation. It's asking for the interval of convergence. I'm going to pass on that here because I'm not going to ask you to do that on the test. The ones that I ask you to find the interval of convergence for, I will give you the summation notation. So I won't ask you to create the summation notation here. So that's just a little bit of extra work that I'm not going to ask you to do. All right, let's see. All right, let's go ahead and take our break unless someone has a question on that part. If not, let's take our 10-minute break, and we'll finish off this power series stuff. Yeah, if you have questions, I'll be here for the break. Let me know. Where are you? That's harder. Where are you? So we're breaking out our tools, and we're going to start building the power series here. So we start with the function, and then we take its derivatives. And they were asking for 4 non-zero terms. So we saw that that meant we have to go down to the 3rd derivative. The 3rd derivative corresponds to p sub 3, which has 4 terms. So there are our first values. And then we plug in our center, and we get the value at the center for each of these. And so the value is either positive or negative, square root of 2 over 2, all the way down. Okay, so That gives us the building blocks for our coefficients. So our coefficients are those numbers, but then we have to modify based on that factorial business. So our function, which is sine of x, is actually equal to the series square root of 2 over 2 plus square root of 2 over 2 times x minus pi divided by 4. So that's the tangent line. Tangent line is the value of the function plus the slope of the function times x minus the shift. Then we go to the next term, minus root 2 over 2. But then we have to divide by 2 factorial. So we're going to put a little 2 factorial in this denominator. And then this will be x minus the center squared. That is our best quadratic approximation, aka p sub 2. P sub 2 goes to the second power. P sub 2 will have 3 terms. And then we go to the next one, p sub 3. We're going to have minus, again a minus. So minus square root of 2 over 2. This one we divide by 3 factorial. This will be x minus pi divided by 4 cubed. So there is p sub 3. 4 non-zero terms, but that's a polynomial. So it's actually not equal yet. This is approximate, but as soon as we go plus dot dot dot, now it's equal. So the series will equal the function, but the polynomial approximates the function. So there it is. And again, if we wanted to find the interval of convergence, we would have to figure out the summation notation and then use the ratio test. Which on the test, I'll ask you to use the ratio test, but I won't ask you to figure out the summation notation. I'll give you that and say, find the ratio, find the interval of convergence. All right. Now, these two are Maclaurin series. And we have already done these. This was the very first one we did, e to the negative x. You can construct the power series for it for sure from scratch. But if you know the power series for e to the x, which that's going to be one of our basic ones that you should absolutely have memorized, the power series for e to the x, to get to the power series for e to the negative x, what do we replace the x with here? Negative x. That's it. And then you have the power series for e to the negative x. So e to the negative x is the power series for e to the x with the x replaced with negative x. Still starts at 0. Now, because we did a substitution, we need to do that same substitution over here. But when we replace this x with negative x here, and then we multiply both sides by -1, we have to reverse the inequalities. We end up with the exact same interval, which we more comfortably write this direction. Now, simplifying this series, because we see this switch inside, we will peel that switch out to the front, -1 to the k, and write this -1 to the k, x to the k over k factorial. So there is the power series for e to the negative x. So here, we didn't do it by construction. We modified a known power series instead of constructing it. So when we say construct the power series, we mean take the derivatives and build it from scratch. We took an existing power series and just did a modification. We don't have to do the ratio test here. When we do, when we are in general, when we're modifying a known power series, we just have to do a little manipulation with the interval of convergence.
Sorry,
Yeah, question?
so with the interval that says minus infinity to infinity, am I understanding that correctly, that it means that for any value of x it's going to converge?
Yes, that is exactly what it means. So if we plug in x equals -5, this will generate a numeric series that converges. If we plug in x equals 12 or 50 or e, any imaginary number even, if you plug in 2 minus I, this will converge. So the interval of convergence tells us the allowable x's that will give us infinite numeric series that converge. So any x for these ones that we're looking at right here. Cosh, well, let's look at e to the x again. So cosine is an even function. So cosine's power series is going to take all these even powers of x, right there. And cosine would have a switch in it. But cosh will take all the even powers straight up. There's no switch. Right? We just take the even powers. The signs all match. All right, so there is cosh. And if we want cosh of 3x, all we do is replace x with 3x. So if we want the power series for cosh 3x, we take the power series for cosh x, replace the x with 3x. And same thing over here, and it's not very interesting when you have this infinite interval of convergence, because when you replace this with 3x, it doesn't change, does it? Right? You divide everything by 3, and you end up with the exact same interval of convergence. And then we would normally simplify this. The summation part, we would normally simplify that. Pull the constant out, so we have 3 squared, which is 9 to the k. And then we have our x to the 2k, all divided by 2k, quantity factorial. And the interval of convergence, you can write it. Either of these methods of writing it is totally fine. You can write it in interval form or inequality form, doesn't matter. So those are some power series.
Do we need to simplify that out to 9 to the k times x to the 2k on the test?
No, you don't have to.
Okay.
You don't have
But we
to,
should.
yeah. Yeah, I mean, when we have a power series, remember that it's sort of like, it reminds me of this, like this right here, if you have a summation, 1 over something like 2 to the k, k to the 2. That's a p series, but if you put a 1 there, it's no longer a p series, it's p series-ish. When you're here, you have to remember that a power series is a series of powers of x. And the way it's written here, you didn't really distinguish the powers of x. So it's better to do this where you have your powers of x kind of isolated off from all the coefficient stuff that's happening. I wouldn't take off for it though, but it's better to sort of recognize that this, you should be visualizing polynomials. Here, it's not quite the same. When you're thinking about this power on something that's not just x, so it's better, but I certainly wouldn't take off for it though. All right. Now we see 2 more where the center is not 0. So as soon as you see the center not being 0, there should be a little bell in your head saying, oh, I need to construct. I can't take an existing power series and massage it. I need to start from scratch. I need to start by taking a pile of derivatives. So that is the key for us in this class, is that if the center is not 0, you need to build that power series. Okay, so we start with the function, y equals natural log of x, and we need to just start differentiating. We get 1 over x. It's easier to differentiate if you write it the way I just wrote it. And 90% of the time they say find 4 non-zero terms. So 4 non-zero terms will mean the third derivative. Next step, we evaluate at the center. And what's natural log of E? Natural log of E is 1, natural log of E. And then y prime of E will be 1 over E. Y double prime of E will be negative 1 over E squared. And then y triple prime of E will be 2 divided by e to the power 3. So this is that same process that we used on Tuesday when we're trying to find polynomials. The same coefficient pattern is used. Same coefficient pattern. Now we can build it. Now we can build it. So our series for f, for natural log of x, will be the value of the function plus the slope of the function multiplied by x minus the center. So that part right there is the tangent line. Value plus slope times shift. That's the tangent line. Best linear approximation. Best quadratic approximation. We just keep on trucking. 1 over e squared, but we have to modify that with the 2 factorial. Multiplied by x minus e, quantity squared. Best quadratic approximation. One more non-zero term. We're going to get plus 2 over e squared, e cubed. And then what's the modifier here?
3 factorial.
Yeah, 3 factorial. And then x minus e quantity cubed. That's our best cubic approximation. Still not a series though. That's p sub 3. That's the third order Taylor polynomial, which will have 4 terms in it. And so to make it a Taylor series, we go plus dot, dot, dot. Now it's a series. Now that equal sign is true. Up until we put the dots, the equal sign is really an approximation sign. It's approximately equal to the function. All right, you all try this one. F of x equals 10 to the x. So same thing we just did up there. Let me go to that, I guess. So build the power series, or build the Taylor series for 10 to the x.
So I understand that at the beginning when we're looking at the equation, we are basically taking the derivative until we get to a certain point.
Yeah, they told us 4 non-zero terms.
Oh, 4 non-zero.
Four non-zero.
Okay, yeah. The first one, the original, and then you plug in what's given to you in there.
And then you plug in the center.
And then you plug it into the center. And then I noticed that when we did a problem where we wrote in the fx and we wrote
Oh,
it
because
in
you know
that
how
form,
in this
the
thing where you have
factorials cancel
that
in
and
some
you're trying to
way,
take
and it
the
was
x
in,
down,
I think it was
so you can
before
like
this
solve for you
was
take the natural log.
Yeah, this one,
Is that like why?
yeah, there's some, it all depends on what the
I
coefficients are. Sometimes it's
Pero sí,
factorial
sí,
can
sí,
cancel.
tendrías un...
We say
And it doesn't, in this case,
Pero ese ejercicio tenías un...
like we could cancel the 2 with the 2 in here. Like 3 factorial is 3 times 2 times 1.
Right.
So the 2's could cancel, but usually we don't simplify the coefficients.
Pero si es así,
You
tendrías
don't
un
simplify
doble...
it.
So
You
it's
see
ln
the
10
pattern.
times
Okay,
10.
question as well.
Mm-hmm.
For this one, I guess there was difference because both of the tests were not.
No,
Well, that's an
ln10
alternating
Times to the
series.
x. So
So
No,
So
no, no,
the,
no, sí, eso al final
the-
que...
so this you can say, so that, yeah, exactly, right there. The limit of that is not equal to 0, so it diverges.
And on this one, the.
Am I like-
Preguntas a ChatGPT.
you have to take the derivative.
How do you know?
Ella is greater than A.
Lo mismo ahí, así que.
So that one's got a smaller exponent.
What's the, is
So
this?
yeah, that's also false. So both are false.
Can I do that?
Yeah, for both of them false. If one of them was right, it would be conditional.
Zero?
No, it's no convergence still.
No,
Oh,
no,
if
if
one,
one-
okay, I'm sorry.
Yeah, if one of them was true.
And
If
zero.
this, if
No.
this limit is not
derivative
zero, then it
of
definitely diverges all
ln10
these.
Always,
that.
oh, guaranteed.
No,
Guaranteed,
zero.
this
that
limit's
one,
not
that's
zero, it has to diverge.
Okay, but this is zero.
No,
Si le
Has
das
to
cross,
diverge. The limit is not zero,
It's-
diverge.
it goes.
Oh, okay. That's fine.
Luego lo hago.
The OneNote worksheet is
You
due tonight
toast that gum.
tonight at midnight. And then we'll review on Tuesday.
We're farming LNs.
Well, it's because you cost a multiple with this one.
All right, let's go ahead and write out our power series,
Sí, sí, lo tienes que obviar.
aka Taylor series in this case. So y equals 10 to the x.
Seguidamos así.
And then the derivative is itself multiplied by natural log of 10. And then the second derivative is itself multiplied by natural log of 10 again, so you get natural log of 10 squared. And then the third derivative is itself multiplied by natural log of 10 again, so you get natural log of 10 quantity cubed. All right, so those are the derivatives.
Qué difícil, bueno.
And now we evaluate them at the center.
Chao, qué difícil.
So y of 2 is 10 squared. Y prime of 2 is 10 squared times natural log of 10. And same all the way down. And now we can build our Taylor series. So our Taylor series will be f of x will equal value of the function, which you could write as 100, plus 100 ln 10 multiplied by x minus the center to the first power. So that is our tangent line. So it's approximately equal to the function. It's not actually equal to the function yet, but then plus 100 times the natural log of 10 squared divided by 2 factorial multiplied by x minus 2 squared. So there's our quadratic approximation. And our last non-zero term, 100, natural log of 10 cubed, divided by 3 factorial, multiplied by x minus 2 cubed, and then we add dot, dot, dot. There is our series. And if we want the interval of convergence for this series, we would have to write it in summation notation and go ratio test. But we won't do that part. Any part of that? Questions? Sebastian?
So, is there any way, or when you're doing the derivative of the original function,
Mm-hmm.
can we switch up like the y's into b into p1 to know like the different points to identify them when we write them? When we
Say
put-
that again, when you take the original derivative, so these guys over here?
Yeah. Can we substitute them for like P1, P2, P3? So then that way we can kind of like identify them when
Sure.
we write them in?
Yeah, absolutely. Yeah, so this right here is going to be P1. Yeah, you can,
Okay.
yeah, you can break it apart like that too. And that is going to be P sub 2. And these are polynomial functions of x. And then if we stop right there, that's going to be P sub 3. Yeah.
Okay.
Yeah. And then we have the whole series, the whole shebang. All right, so let's do something that's a little bit new, I would suspect. If you've taken a stats course, you've seen these weird coefficients. So these coefficients are called binomial coefficients. It's right there. And again, if you've done stats, you know what it is. If you haven't, then this might be new to you. So the definition of a binomial coefficient is this. So it's not a fraction, it's just P choose K.
Is it like a matrix?
It is,
Tiny?
say, I wouldn't consider, I understand what you're asking. I would not call it a matrix. They
Okay.
usually just call it a binomial coefficient. It does have that matrix look to it though, right? Because there is not a fraction bar. So it does look like a 2x1 matrix, a column matrix. When you get into dealing with vectors, this is the notation that you would use for a column vector, which is a matrix that has just one column. But yeah, we usually would just refer to these as binomial coefficients. But it does have that same shape. And this is the definition right here. You take the upper number, form its factorial, you divide it by the lower number, factorial, and then you take the difference and you get a factorial. So that is the definition of a binomial coefficient. All right, so let's just do an example of that first. So if we have something like 6 choose 2, that's what that means. That's how you say it, 6 choose 2. And what it's giving you is the number of ways, if you think about a stats course or a probability course, if you had like a box and there were 6 balls in the box and you picked 2 out, this is going to tell us how many ways you could pick 2 balls out of a pile of 6. So that's what this would physically generate. So this is 6 factorial over 2 factorial times 4 factorial. But if you notice, 6 factorial is really 6 times 5 times 4 factorial. And so you can kind of say, oh, well, there is a cancellation here. Okay? And these binomial coefficients, when you're doing them in an algebra class, everything is an integer. And so you get a 15 here. So there's 15 different ways to pick 2 things from 6 things. So if you have your 6 balls in the bag, 1, 2, 3, 4, 5, 6, there are going to be 15 ways that you can pick 2 out of those 6. So that's what that's the physical interpretation of a binomial coefficient. But they're all integers, right? And we are going to see that you can change that in a minute. And you don't have to have integers. So, how many of you have seen Pascal's triangle back in algebra? A few of you have seen it, not everybody though. Some of you have not seen it. Somebody raise your hand if you haven't seen it, just so I have a sense. So Pascal's triangle, the way you form it is by adding the 2 numbers directly above to get the number below. So we would add these 2 numbers to get to that number. We'd add those 2 numbers to get to that number. So it's got this little sort of funneling method to create the subsequent rows. And the application of Pascal's triangle is super cool. Back in the day, we always covered this in algebra. It gives you a shortcut for finding the coefficients if you were to square a binomial in this case. So if you take a plus b and you square it, you get 1a squared plus 2ab plus 1b squared. So the 1, 2, 1 coefficients are right there. If you were to raise it to the 3rd power, those are the coefficients. So you get a cubed plus 3a squared b plus 3ab squared plus 1b cubed. So this gives you a way to take a binomial, a plus b, and raise it to an integer power. So these are the coefficients. So this is the coefficient for the square, coefficients for cubing, coefficients for 4th power, coefficients for 5th power. So a plus b to the 5th power will have those coefficients. So Pascal's triangle is kind of cool. It gives you a shortcut for doing things like that. So there is a good example. So 1 plus x to the 5th. So we are going to have 1, 5, 10, 10, 5, and 1. Those are the coefficients. And then the power of x is going to be 0 right here. Power of x is 1. Power of x is 2, 3, 4. So the x's power increases all the way through. Well, those coefficients are found this way. This is 5, choose 0. This is 5, choose 1. This is 5, this one, I'm confused here. Where am I looking at? Those arrows don't seem to be, oh, I think I stretched the board. And so they're not, oh, I don't know what I did. They don't seem like they're lined up right.
They go to the equal sign.
Oh, okay, yeah. So 5, choose 0 is this one. 5, choose 1 is this one. Okay, they're lined up. 5, choose 2 is this one. 5, choose 3 is that one. 5, choose 4, and 5, choose 5. Okay, so it is lined up fine. Lined up fine. So that's another way to find those coefficients that are in Pascal's triangle. So if you use Pascal's triangle, you can just do this cool kind of trick where you're just adding the two numbers above. But in general, those coefficients are found with these binomial coefficients. Okay? So another example here, 8 choose 3, you just pull the 8, pull the 3, take the difference, factorial everything, cancel it out. What I want you to notice is that right here, similar to right here, you can sort of imagine rewriting the definition of the binomial coefficient so that there's not a factorial in the numerator, right? Because this cancellation pattern is always going to happen where you can chop the numerator's factorial off by canceling with this, in this case, the 5. Peyton, what are you doing?
I don't know.
Something's happening. So what this allows us to do, one thing we do in math all the time is we use some physical phenomenon and we create a definition. And then what mathematicians love to do is stir it up. And so what we're going to do is stir this up and make it worse by doing this kind of thing where we get rid of the factorial in the top. Now we see in the top you don't have a factorial anymore. And so you can imagine putting a weird number there that's not a positive integer because the factorial is gone. And the pattern is that you do repeated subtraction of 1 until you have this number of factors, 3 in this case. Up here, I have a 2 down here, so you can imagine this as 2 factorial, and then in the numerator we start with the 6 and we do repeated subtraction of 1 until we have 2 factors. So we have this pattern that we are going to take from the simplified form of the binomial coefficient. So for example, if we want to get weird here, we could say, hey, let's put a non-positive integer there. The denominator just becomes whatever the lower number is factorial. And the numerator, we take the initial number, right there, 8 in this case, repeated subtraction by 1, this, until we have that number of factors. So we take the negative half, we subtract 1, we subtract 1. Now we have 3 factors in the top. And now we get a value for this binomial coefficient that's not really a binomial coefficient anymore because we don't have a positive integer in that top position. But it generalizes what these coefficients do, which leads us to a little more madness called the binomial series. So that is the binomial series. That I would never suggest memorizing. It looks horrendous. Even trying to understand it is difficult. What I'm going to say is this. That is what you should think of right there when you think of the binomial series. Think of this. So the binomial series, we take a binomial raised to a power. The power does not have to be a positive integer. It can be a negative number. And this is what the binomial expansion looks like. It looks exactly like the geometric series. 1x, x squared, x cubed, x to the 4th, etc. It's just that you have these coefficients. So we have these coefficients. So it's a modified geometric series. It's a geometric series where the coefficients are found in this obscure way. That is what you should visualize when someone says binomial series. Don't try to visualize that thing up there. That's horrible. Now, the question, the obvious question, what x's does it converge for? Right? That's what we've been spending the last month doing. What are the x's that give us convergence? And that is a very hard question. That is given to us. If the p is less than or equal to -1, the interval is -1 to 1. So I will give you these intervals. We do not have the mathematical ability at this point to even show that these are the intervals of convergence. Take some extra math. Because these binomial coefficients are just weird enough that it takes some very abstract math to get at the interval of convergence for these different values of p. So these will be given to you. So those are our 3 possible intervals of convergence. They all have goalposts, -1 to 1. Less than or equal to -1, everything is open. If you're between -1 and 0, you get a closed on the right. And if we are greater than 0, we get closed on both sides. So those are the 3 possible intervals of convergence. What this allows us to do is look at some really funky functions. So we look at this function, square root of 1 plus x, and if I asked you to build the power series for it, or the Taylor series for it, you would say, oh gosh, I've got to start taking derivatives, right? Take 4 derivatives or whatever you need. Total pain with a square root. But if we recognize that, oh sheesh, it's just a binomial raised to a power, right? This is just a binomial. Binomial is 2 terms. Raised to that power. Then we can just do the binomial expansion, and we already know the interval of convergence. We are going to save a lot of time. So here is how we should think of this. So the p-value is 1/2, p for power, p for power. So we are going to have, and this is how I will rewrite it all the time. So there's our first coefficient, the constant term. Then we have 1/2 choose 1, and it just climbs up just like we do with a geometric series. All we're doing is modifying the coefficients of what otherwise looks like a geometric series. So this is what we're trying to simplify. And does it say first 4 non-zero terms? 1, 2, 3, 4, that's enough. But it's a series, so I'm going to put the plus ... to emphasize that it is a series and not just a polynomial. So this says first 4 non-zero terms of the binomial series. Does not say anything about a polynomial. So make sure when we're talking series, anytime we're talking series, make sure you've got these dots just to emphasize it's a series. All right, so there it is. And now this p-value is positive 1/2. So if we look up here, positive 1/2 is in this interval. So -1 to 1 closed is our IOC. So -1 to 1, that is our IOC. I should write I equals that thing. So I equals that. Interval of convergence. All right. Now with these ones, there is no way to write it in closed form other than that hideous way that we saw above. So with a binomial series, we always are leaving it in expanded form. So just multiply it out. 1/2 choose 0. Question?
It says the first 4 non-zero terms, but wouldn't the 1/2 0 be 0?
No.
Is it 1 then?
Yes.
Okay.
So if you think about the bag thing, if you do a choose 0, like if you say, let's suppose we have the bag of balls with 5 balls in it and you choose 0. There's one way to do that, and that's to not choose anything. So any p choose 0 will always be 1. So that's always going to be 1. And so 0 factorial feels like you might want it to be 0, but 0 factorial is going to be considered to be 1. Now, it's not intuitive though, but if you make that a definition, that 0 factorial equals 1, then it just makes all of the notation work absolutely seamlessly. Even though 0 factorial feels like that's probably, like in the real world, 0 factorial feels like, how can that possibly be equal to 1? We define it to be 1 for all of our notational purposes. 0 factorial will be 1. It just makes all the notation work fine, even though it feels counterintuitive. So that will always be 1. This will always be p. So this will always be whatever p is. So these two terms, the first two terms, generally are super fast. It's usually 1 plus p times x. All right. Now we have to do a little bit of work on these two. So let's come off to the side and do 1/2 choose 2. So 1/2 choose 2. The denominator is 2 factorial. The numerator starts as 1/2. And then we start subtracting 1. We do repeated subtraction of 1. But we are done already because this is just a 2. So if that's a 2, we stop after we have 2 factors. So we're done. So this is going to be negative 1/4 in the numerator divided by 2, which is negative 1/8. So that is what's going to go here. Negative 1/8 times x squared. And then we're going to do the 1/2 choose 3. So 1/2 choose 3. Same idea. The 3 is in the denominator as a 3 factorial. The numerator starts at 1/2. And then we do repeated subtraction of 1. And when do we stop? Well, we stop as soon as we have 3 factors. So that will be the numerator. Just repeated subtraction of 1 until we get to the spot where we have, in this case, 3 factors. So our numerator is now positive. It's going to be 3/8. The denominator is 6. So when we simplify this, we have 3/8. Dividing by 6 is multiplying by 1/6. We get a 2, so we get a 16th. So that is going to be our power 3 coefficient. So 1/16 times x cubed plus etc. This goes on forever. So that is our series expansion. So we found the series for root 1 plus x using a binomial expansion. If you were so inclined, you can take this function and start doing repeated derivatives, and you would build the exact same series. Same exact series would come if you started taking 3 derivatives and plugging in the center. The center here is 0. Right, the center is 0. It's all just powers of x. All right. So now it's saying we want to approximate that. All right. So we're going to approximate that. We can think of this as the square root of 1 plus 0.06. So for us, the x is being represented by 0.06. So our approximation, so we would say that the square root of 1.06 is approximately equal to 1 plus 1/2 multiplied by 0.06 minus 1/8 times 0.06 quantity squared plus 1/16 times 0.06 cubed. So that's going to be our approximation. So if you type that into your calculator, if someone has a second to do that, that will be our approximation, whatever that turns out to be. Okay, so let's take a look at this. We have a binomial raised to the -3. Here we have a binomial raised to the 2/3. So whenever we have these binomials, that's a clue that we can use the binomial theorem or the binomial series. This could be done by taking multiple derivatives. That would be a real headache to take multiple derivatives of that, of either of these. It would be a real pain. So what we're going to do instead is this. We're going to say that 1 plus x to the -3 is going to be, what is p? P is -3, right? P is the power. So this is going to be -3 choose 0 plus -3 choose 1 times x. So when we write our 4 non-zero terms, it's always going to feel like a geometric series type expansion. And then we can stop at the cube, but make sure we put dot, dot, dot because it is a series that we're looking at. -3 choose 0 is 1. -3 choose 1 is -3. So the first two terms are immediate. So let's come off to the side and figure out what -3 choose 2 would be. Whoops, not a fraction. No fraction. So -3 choose 2. 2 factorial in the bottom. Top, we start with -3. We do repeated subtraction of 1 until we have the number of factors indicated by that denominator. That denominator is a 2, so we stop at 2 factors. We get a value of 6. So this will be 6x squared. So there is our best quadratic approximation to that binomial to the -3. And then we have to do -3 choose 3. -3 choose 3. The numerator will be -3 times -4 times -5. Denominator will be 3 factorial, which is 3 times 2 times 1. So whatever that simplifies to. The 3's cancel. And the 2 goes into 4 twice. So we're going to end up with -10. That will be there, and then plus dot, dot, dot. So there is our binomial expansion. The p-value is -3. And if we go back and look, the IOC here will be -1 to 1, and we're going to exclude the endpoint. So that's going to be given to you. Say again?
Is the 10 positive or am I looking at the wrong?
This 10 is going to be negative because we have 3 minuses being multiplied together. So I canceled the 3 here, but not the minus sign. So it's going to be minus, 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 which will end up leaving us with a negative. You see it? So it will be negative. And you can kind of see that we are going to have an alternating series because we're going to keep putting another negative every term we go out. So we'll end up alternating the terms. So now let's try one with this fractional exponent of 2/3. So again, my recommendation is the first step, just write out the generic series like that. So our p-value is 2/3, so we're going to start with 2/3 choose 0. And then we're going to have 2/3 choose 1 times x, and then we're going to have 2/3 choose 2 times x squared, and then we're going to have 2/3 choose 3 x cubed plus etc. So there is our generic expansion. And then we just need to simplify those coefficients so that they are fractions or integers or whatever. The first two are always instant. 1 plus px. Those two are always pretty easy. And then we come off to the side, we'll do 2/3 choose 2. 2/3 choose 2. 2 factorial down below. Numerator, we're going to have 2/3, and we subtract 1 and get negative 1/3. So we're going to have negative 2/9 divided by 2, which means multiply by 1/2, and we're going to get negative 1/9. So that will be this coefficient. Negative 1/9 times x squared. Cool. So now we've got our best quadratic approximation. That's p sub 2. And then to get p sub 3, we're going to need 2/3 choose 3. So everything's going to look the same except that we have 2/3 times negative 1/3. And then we subtract 1 again. So that will give us negative 4/3 divided by 3. So whatever that simplifies to. So that looks like it's going to be positive. That's going to be 8 divided by 27 multiplied by 1/3. So 8/81 will be that next coefficient. So plus 8/81 x cubed. And we can put a minus there. We know it's going to be negative. It doesn't matter if you put minus or plus. Yeah.
So in the numerator, when you, for example, the 2/3 and the 2, the number of
Factors.
factors that are going to be on the numerator is the amount that you have in the denominator for factorials.
Yes.
So if there's 4 of them, if it is 4 factorial, then it's going to be 4 in the numerator.
Yes.
Okay.
Exactly. Exactly. So that number in the lower number, the number that will turn into the factorial in the denominator, tells you how many factors in the numerator you will have. That is right. And then our IOC for this one.
It's 481st.
So this was positive 2/3. So this is question.
Could you really quickly go over why the 3 factorial went away?
Yeah, it should be over 6.
Oh.
And then it would be 481st.
Thank you. Yes, great question. That should be a factorial, so that should be a 6.
And that should be a 481st.
And so that should be, that we're going to cancel out a 2 goes into there, so we're going to get a 4 right there. Thank you. Good catch. Very good catch. So that will be a 4. Yeah, thank you. Good call. All right, and then what about the IOC? So we look at our p-value, 2/3, and that is positive. Does that include?
So it includes both.
It includes both, right? When it's positive. So we have that.
P is greater than 0.
P is greater than 0, so we include both, right? And then P less than negative 1, we include nothing. And then in between, we include just 1, just the right endpoint. So the binomial series ones, if you practice a few of them, they should start to be pretty routine. They should be a little easier than what we did earlier today. Much easier. So let's look at a couple more examples with the binomial. Oh, there's the one we just found, right? We just calculated that a moment ago. So here's binomial series. There's an expansion. The p-value is 1/2, which is greater than 0, which is why they're including both endpoints on the -1 and 1. Now, let's be careful about the reading of this. This one's a little odd. So we have, we want to use a Maclaurin series. So Maclaurin series is centered at 0. Okay? Maclaurin series is centered at 0. So, the first thing that you might want to do is this. You see that 1 plus x there? It feels like you should rewrite this square root like that. Okay, so if you did that, then wouldn't you be replacing all these x's with 3 plus x, or if we wrote this like makes more sense in this context, we normally would write, if we're doing a shift, write it as x plus 3. Obviously they're the same. But you would replace all those x's with x plus 3. Is that a Maclaurin series? If all those x's get replaced with x plus 3, would that be a Maclaurin series? Would that be centered at the origin? No, it'd be centered at what?
Negative 3.
-3. So they want a Maclaurin series. So that is a great guess, and we could create a series centered at -3 by doing what we would be doing next. But if we want a Maclaurin series, we are going to have to somehow change this to a 1 in another way. What would that other way be? How else could we turn that into a 1? Favorite math F word? Factor. So if we factor out that 4, it comes out as a 2, and then we'd have 1 plus x divided by 4. And so that's kind of what we've been doing earlier in the semester when we were doing, I forget what we were doing, some sort of integration technique.
Trig sub.
Trig sub! That one. Oh man, I blocked that out of my mind. So now, when we go to create our series here, we have a 2 multiplied by, now we're going to replace the x with x divided by 4. So we're going to have 1 plus, this x gets replaced with x divided by 4, so we'll have x over 8. The next one gets replaced, so we're replacing that with x over 4, so we're going to get x squared over 4 squared. 4 squared is 16. And then 16 multiplied by 8 is something. Let's see. 8 times 16, that's not right, is it? So let's see, what am I doing? 16 times 8. 16 times 8. So that's 48, that's 128. 128. Goes there. Oh, the hard math. And then x cubed. So now we're going to have 4 cubed, which is 64. And then 64 times 16 is?
56.
64 times 16. I'm just going to write it like that.
1,024.
Is it 1024?
Yeah.
It's just power of 2's. Right, good point. All right, and then this is going to go on forever. So there it is. That is our Maclaurin series because we just have powers of x. We don't have x minus something or x plus something, so that's a Maclaurin series. The other one was not a Maclaurin series. And the IOC is that modified because we did a substitution. Right? Anytime we do a substitution, we got to be careful. So we substituted. So here is the original IOC. But we substituted x divided by 4. So we're using that technique of substitution. If we substitute, then the new IOC gets modified. Anytime we do a substitution, there is our modified IOC. So there is our Maclaurin series with the new interval of convergence. So we use that same rule of substitution regardless of what the original interval of convergence is. Anytime we do a substitution, we've got to modify the IOC. Okay, here's another binomial. Here we're going to replace x with negative 4x. So negative 4x. So we look up there. We have 1. Negative 4x over 2. I'll simplify it in a second. You don't have to simplify these. And then we plug negative 4x in for the next one. So we get minus. And then when we square that, we're going to get 16x squared over 8. That's the third term. The next term is plus, no, minus, because it's a cube. So we're plugging in 4x there. We're going to have something over 16. 4 cubed, so 4 times 4 is 16, times 4 is 64. X cubed
All of your leading terms are 2.
plus 0. Oh, nice.
Oh wait, not for the third one.
Yeah,
First 2 are.
there we go. The first two. Yeah, so if we simplify it, we'll end up with that. Yeah, it feels like
That
it's going
one's
to
a
be,
4 though.
seems like it was going to be a good pattern at first. But. So there is our expansion. We can't write it in summation notation unless we use a really horrible notation that we don't want to deal with binomial coefficients. So an expanded binomial series is how you're just going to leave it, first 4 non-zero terms. The IOC then needs to be modified. It started at -1 to +1. And then we replace the x with -4x. So then we come through and modify this interval. If we divide everything by -1/4, remember to switch the inequality. But that really is the same thing as this, which is a little more readable. So that will be our interval of convergence. You can write it in whatever that form is, inequality form, or you could write it in interval form also, doesn't matter. Whatever you're thinking. So there is our series with its interval of convergence. Okay, so binomial series. And the last thing that we're going to do in this culminating chapter is more of a, like, oh, interesting. It's not super technically difficult. It's just, oh, you know L'Hopital's rule, right? You have an indeterminate form, take a limit, take derivatives, take the limit again, right? L'Hopital's rule. But check this out. We can use, now that we understand power series, anytime we're taking a limit, we can use a power series instead of some other technique. Now, it's a little more work than L'Hopital's rule in this case, but we can do it. So if we take the power series for sine, which are the odd powers from e to the x with a switch thrown in, there it is, sine of x power series, we're dividing by x. Cancel 1x everywhere, and we have the limit of this as x goes to 0, not infinity, 0. That limit's 1. Okay? So you can now do limits with power series. We'll do one more. So here is the power series for arctan, right there. Odd powers of e to the x with a switch, but then no factorial, so it looks a lot like sine. If you divide everything by x cubed, so you're going to subtract off x. So if we subtract x, limit of x goes to 0. So this x is going to cancel with this subtraction of x, and then we're going to divide by x cubed. So if we divide by x cubed, we are going to end up with and what is that limit as x goes to 0?
1/3.
-1/3. Yeah. Done. So if we replace that inverse tangent with its power series, we do this subtraction of x, that thing is gone. And then we divide everything through by x cubed. X cubed goes into x cubed once, goes into x to the 5th that time, and that. Limit as x goes to 0, we get -1/3. So this section, the last section is kind of trivial because you can just treat your power series like a polynomial. All right, well, let's stop there. See you next week. Have a good weekend. Enjoy the warmth.
Do your worksheet.
Do a bunch. Oh, worksheet due tonight at midnight. which really means tomorrow by, oh, I'm gonna be in a conference all day tomorrow, so I'm not gonna do jack until tomorrow night.
Cool, so tomorrow.
But tomorrow's Friday night, so I'm playing poker, so it's really due Saturday morning.
Saturday at noon.
Which really means Saturday at noon. Good point. Oh yeah, good call. Oh, yeah. Stuff's happening, man.
Ismael, mi mejor amigo.